Welcome back. So, in the last couple of classes, we discussed varieties of things about analysis of the spectra, spin nomenclature, multinuclear NMR, and varieties of interesting things we discussed. But there is one important thing which need to be understood, especially when we studied carbon 13 NMR, silicon NMR, and nitrogen 15 NMR. There are low abundant nuclei. We already discussed the sensitivity depends upon gyromagnetic ratio and also on the natural abundance. So, how do you overcome some of these problems? There is an inherently NMR technique compared to other spectroscopic technique is insensitive. Added to that, detection of such low abundant nuclei poses additional challenge. So, there are many stalwarts and pioneers in NMR have come out with numerous methods and technologies to circumvent some of these problems to a large extent. And one such thing is polarization transfer. What it means is we take the magnetization from abundant spins and transfer low gamma nuclei. What it means, rob the rich and pay the poor. Then what will happen? The magnetization of the low abundant spin goes up and we can detect with better sensitivity. This is one of the ways. So, and we can combine this thing also for doing spectral editing. This polarization transfer technique is invariably used in heteronuclear NMR, especially direct detection and inverse detection techniques, etc. So today let us discuss something about this polarization transfer technique and spectral editing both. So these are all some of the important things, especially when you are dealing with two-dimensional techniques which we are going to discuss later, where we use HSQC and others, where polarization transfer is extremely useful when we do inverse detections. So today my focus is on polarization transfer and spectral editing. First thing we need to understand for this, the basic requirement is a spin echo technique. This is one of the important things modules in NMR. What are spin echoes? If you understand the spin echoes, lot more things about polarization techniques and spectral editing techniques can be understood. And this spin echoes, what I am going to tell you now, is a small pulse sequence module which can be incorporated in many experiments, and it does a specific job. It is a combination of pulses with some delays and performs a specific job. And we can have several types of experiment we can do. Using spin echo, what we can do is we can control what are the changes that occurs because of chemical shift only. We can get changes during the day. We can set a delay between the pulses, and during this delay what happens, I'll explain to you when you go ahead. We can ensure, we can find out whether only chemical shift will refocus or only J coupling will refocus. What is going to happen during this delay, that can be understood. And this such a module is so simple and a small module. You can put it anywhere in your complex spectrum, complex pulse sequence, so that you can manipulate this evolution of magnetization in different pulse sequence, and you can get whatever the predictable information you want can be obtained. See, for example, I can use the pulse sequence, I can plug it here into one of the pulse sequence, and let us say it does a specific job, what I want. It can be predicted, and I know what is the desired output of the pulse sequence. So these things we can manipulate by using spin dynamics. And for many of the cases, we come across what is called spin echo sequence. So let us discuss something about what is a spin echo. The spin echo sequence is something about chemical shift refocusing. I am talking. What it means is, look at this. It is a very simple pulse sequence. We have a 90-degree pulse. We already discussed about what is a 90-degree pulse, what is a 180 pulse, and I also discussed about the ways we can apply the pulse sequence pulses. We can apply pulse along x-axis, pulse along y-axis, phases of the pulses, we discussed long back. Okay, in one of the classes. So 90-degree pulse bring the magnetization from z-axis to xy plane, either x-axis, y-axis, depending upon where I am applying the pulse. Then we give a small time delay called TD. What will happen during this time, we will see. And after that delay, we are going to apply another 180-degree pulse, give some more delay, exactly equal to this one, and then start collecting the signal. Remember, in a conventional experiment, what you are going to do is apply a 90-degree pulse and collect the signal. That is a one-dimensional experiment. What we do here is, spin echo, we incorporate another 180-degree pulse in between with delays after 90 and after 180-degree pulse, and then after a sufficient delay, which we know, we will decide what is TD, time delay, and then collect the signal. TD is nothing but a time delay, that's all. Now, let us vectorially understand with a vector diagram what happens to this magnetization during this pulse sequence. Of course, just before the application of a 90-degree pulse, what is the status of our magnetization? It is in thermal equilibrium and along z-axis. We understood the bulk magnetization concept. Please remember that bulk magnetization concept. Magnetization is along z-axis. Fine. Now, I am going to apply 90-degree pulse. What happens to that? This 90-degree pulse brings the magnetization depending upon where I am applying. I am applying 90-degree pulse along x-axis. Then magnetization has to tilt, the flip along minus y-axis. This is because of the right hand thumb rule I discussed. So remember, the thumb will point out the direction of the pulse, and the magnetization tilting is defined by the curly fingers. For the direction in which the four fingers get curled. For example, this is the magnetization is here. Now I am applying a pulse along x-axis here. Then what will happen? This is x, this is y, this is x, this is y, and this is z. So I am applying a pulse along this axis. So magnetization along z-axis. If I apply pulse along this axis, what will happen? Magnetization will tilt in the direction of the curl fingers which get curled. So that is, this is plus y, this is minus y. So this we have understood. I don't want to explain every time these things. Please remember, now the 90-degree x pulse will bring the magnetization to minus y axis. Okay. Now what is going to happen? As soon as you bring the magnetization 90 degree to minus y axis by a 90-degree pulse, we keep quiet. We don't do anything. What we will do is, we will allow this magnetization to start dephasing with the time TD. Remember, I discussed about dephasing. As soon as the magnetization is brought to xy plane, initially the entire magnetization will be in coherence. All nuclear spins, magnetic moments will be in phase. There is a coherence. There is a phase coherence, I told you. What happens? Due to various phenomena, this nuclear magnetic moments start dephasing. This we discussed. I call this as a relaxation time T2. Please remember. So the spins start dephasing. How do they dephase? They dephase, start moving like this. Okay, like this. At the end of the first TD, the spins have higher frequency, larger frequency, rotate forward, and lower frequency, rotate backwards. You remember, with respect to the rotating frame of reference, we discussed entire magnetization is initially along this axis, all the nuclear magnetic moments. Now, because when they start dephasing, some will start moving like this, some will start moving like this. With respect to the on resonance frequency, this is our carrier offset, let us say. With respect to this, now the spin packets or vectors in this direction start moving like this. The vectors here start moving like this. This is called a fast moving component. This is called a slow moving component. So with respect to this omega naught, let us say I call this as omega naught, the spins with a higher larger frequency moves faster. Spins with the lower larger frequency start moving. That's what is, in the rotating frame of reference we understood. This is omega naught. These are all different normal frequencies. So this is moving with the higher frequency, this is lower frequency, this is faster component, this is slower component. Okay. Now after a certain time TD, what is going to happen? Okay. So what is going to happen is after a certain time TD at this place when it is completely dephased, I am going to apply a 180-degree pulse here. This one at this point. When I apply 180-degree pulse, what is going to happen? I am flipping the nuclear spins which were like in this axis. I'll rotate it like this. Remember, it is like turning the pancake. You're turning a pancake like this. If the light was like this, it was, or in the Indian breakfast, this is dosa. You can turn the dosa like this. So this is what the role of the 180-degree pulse. It flips the magnetization from minus y-axis to plus y-axis. Okay, because I'm applying the pulse along x-axis. Remember, I'm sitting here and I can rotate like this. When I rotate like this, it rotates by 180 degrees. Now what is happening? They continue to move in the same direction. In that case, what happened? The spin labels get interchanged. So when it put it like this by a 180-degree pulse, when you change this completely, invert it like this, the fast moving component starts moving slowly, slow moving component starts moving faster, because they continue to move in the opposite direction now. Okay, the one which was going like this will continue to move in the same direction. Now with respect to this axis, the fast moving will be moving slowly and slow moving component will start moving fast. They continue to move in the opposite direction. 180-degree pulse, you understood what happened? So what we did is we simply rotated the magnetization from minus y to plus y axis. We interchange the labels of the spin vectors. So fast and slow moving components just gets interchanged. As far as the precision is, as far as the movement is concerned, the one which is moving like this fast will move slow now. The one which is moving like this slow will move faster. Now wait for another time TD. This is called a second time delay. After some time, what happens? All the spins get refocused. Okay, it is, imagine, different spins will be moving in different speeds. One may be moving fast, one may be moving faster, one may be moving fastest. Similarly, one may be slow, one may be slower, one may be slowest, and they are all moving at different frequencies. Then what happens when you allow them to exactly same amount of delay when it is given? They come back and start refocused here, the same on the y-axis. Imagine a condition like this. Now there are 10 people are standing in the queue, are standing in the row. 10 people who are runners. There is a running race going on. As soon as a whistle is blown, all 10 people who are standing in the row starts running. Of course, all of them not having the same speed. Some will move faster, some will move slow. Exactly like what I said, like the spin vector components. And after some time, immediately I'll ask them to stop, wherever they are. Then I apply 180 pulse. 180 pulse means I will invert it. Okay, I will rotate the spin. So I will ask them to turn back. All the spinners, all the runners who are going there, wherever they are, they turn backwards. That is the effect of 180 pulse. Now I will ask them to run back, continue to run. What they will do? They will start running. Their speed remains same. Okay. Now one was fast, one was slow, doesn't matter. One was fast, moved fast, that fast. One was slow, was like this. Now they continue to move in the opposite direction. Finally, what will happen? It appears to you as this. The person who was slow is already moved faster. He has come, and person who was fast is already slow, is behind. You understand? After some time, then what happens? At the same amount of time, although they were different speeds, they come back to the same at this point of starting at the same time. They start at this point, they come back to this point at the same time. This is what is called refocusing. This is echo. This is called echo. So that means all the spins get refocused. This is what is called, in effect, a spin echo where we have refocused the chemical source. Understand, this is the concept of echo. 90 tau delay and 180 tau delay and correct the signal. This is an important module called spin echo module. Okay, so the spin vectors which were moving in different normal frequency, one moving faster, one moving slower, like that, gets inverted as soon as I apply 180 pulse. Simply turn it from minus y to plus y. Spin labels get interchanged. They start moving backwards and refocus at the same point where it started, and they are all in phase again. They face the decoherence, disappear, they all come back to the same phase. This is what is called spin echo. This is the animation of that, which is taken from the Wikipedia. You can see that this is what is happening. Look at it, the spins are like this. You apply a 90-degree pulse, bring it to x-axis or y-axis, they start dephasing like this. 180 pulse, rotate like a pancake, and then start come and you will refocus with the maximum signal there. That is called an echo. Okay, so now we will see the 13C spin echo pulse sequence and the decoupling we want to see. See, this is the 180 pulse sequence. We understood what is going to happen. Now I want to see 13C signal. This pulse sequence I apply. I am going to detect the signal by decoupling. I explained to you, when I am looking for the carbon 13 NMR, normally we do the broadband decoupling and detect the signal, right? This is the pulse sequence. This is the spin echo sequence, and then we are collecting the signal here with proton decoupling. In this channel, we are going to apply what is a decoupling. I explained to you some time back, but in any case, what I am going to do is quickly I will tell you what is decoupling in just 2-3 minutes or 5 minutes, so that we can continue to go further. Okay, I already told you, and then I don't need to come back to this decoupling. So one of the important problems I said in the carbon 13 NMR is the detection of low sensitivity. It takes enormous amount of time, and especially when the signals, when the carbons are coupled to protons. Okay, so first thing is it takes larger experimental time because of various reasons. A long relaxation time, low sensitivity, etc. And what we have to do is you do the decoupling, break all the couplings of protons with all the carbons simultaneously, so that you will get only single peak for each carbon. How we do this? We can suppress this by a broadband decoupling, where RF power, second RF power is applied to cover the whole range of proton frequencies. I told you when I explained to carbon 13. Just quickly, I don't want to come back to decoupling again, so I'm repeating it. I'm telling you. Now, let us look at the proton spectral width of 10 ppm. Sit at the center of the proton spectral width, that is at 5 ppm. Apply RF pulse in such a way it has a wide range of excitation profile. Such a RF power of the pulse you have to apply in such a way, the excitation profile is so broad, at the same time as uniform power. You have to choose. See, the square, rectangular pulse or square pulse you are applying. If you do the Fourier transformation, in one of the classes we showed, I discussed the Fourier transformation of that is a sinc function, where we can see at the exactly at the center, where we call it as omega naught, or call it as a carrier frequency, the power spectrum is more or less is uniform. It is a broad. It is really broad at the center. Take that region where the power is uniform. Apply a pulse. Choose the offset in such a way. Apply a pulse with the so that the excitation profile is uniform. Then what happens is, at a given instant of time, all of at a time, you are breaking the coupling between protons and all carbons. And this is called heteronuclear decoupling. What happens is, conceptually it is like this. Irradiation causes proton to get saturated. What is the meaning of saturated? I told you the spin population becomes equal between two energy states. The proton energy states, spin population become equal. In other words, they undergo rapid transitions among all the possible spin states. What does it mean? When then the coupled spin carbon 13 do not see the proton in either of the energy states because of the rapid transition. It doesn't see the proton spins residing either in the alpha state or in the beta state. And you are applying the power in such a way, you are saturating, making the spin population equal, and there is a rapid transition undergoing on. As a consequence, the detected nuclei carbon 13 will not see proton in either alpha state or beta state. So it breaks all the coupling. So it is as good as telling there is no energy separation at all. Like a degenerate state, as far as carbon is concerned, there are no two spin states for the proton. That's what happens. In effect, all the spin interactions are averaged out between carbon and proton. All means between carbon and proton because of this rapid changes. Then carbon nucleus senses only an average spin state for the attached hydrogens. Okay, that's what I said. It appears as if there is no degeneration of the energy state, and as a consequence, we don't see coupling at all. Each carbon does appear as a singlet. The question now is, how much is the decoupling power? You have to apply the decoupling power in such a way the decoupling power should be larger than the coupling strength. What is the coupling strength? If you measure the J coupling between carbon and proton, it can be 100 hertz, about 150 hertz, 200 hertz, 250 hertz. Then which one you choose? Choose the power such that the largest J coupling, the power should be larger than the largest J coupling between carbon and proton. That means automatically that power is sufficient to decouple all carbons with protons. So what you have to do is, decoupling is simple. Set the decoupler offset at the center of the proton frequency. Apply another radio frequency pulse. It is called a decoupler pulse. In such a way, the RF of this, the power of this pulse, so it should be gamma B2, must be larger than the coupling strength, largest coupling strength you do. And then when you do that, I showed this example, all these multiplicities. For example, the CH3 is a quartet, reduces to a singlet. CH2b is a triplet because of this CH2 carbon, because of two protons, it is a singlet. And this is CH2 is also a triplet, reduces to a singlet. So all in the carbon spectrum, you always see the coupling between carbon and directly attached protons. Again, using the 2Na+1 rule, you know, is a quartet, triplet, and all these carbons are doublet because of directly attached protons, and this multiplicity reduces to singlets like this. And this is what I said, and there are various processes of decoupling also I discussed, like gated decoupling. I remember, I don't want to go again, because now I'm discussing about the carbon 13 decoupling in the spin-echo sequence. I just wanted to complete the decoupling topic so that I don't need to come back again. So we had again, you can apply the decoupling power before RF pulse. We call it where the coupling is retained. There is no decoupling power during acquisition. It is a coupled spectrum, and when you apply a decoupling power before the RF pulse, this pulse creates what is called NOE. Next topic of my discussion after this talk is NOE. I'll discuss more about NOE. And we can do this like this. Here you don't apply power, you apply power only during acquisition. This is, you are going to get, there is no NOE but only decoupling. This is a decoupled spectrum without NOE. You can also do power decoupling, that is continuously keep applying the power. Then you are going to get decoupling on throughout the experiment. This decoupling and NOE experiment. This is the routine carbon 13 spectrum what you do. And this is what we see. And there are a number of ways of doing the decoupling. And I don't want to tell you all those things. But decoupling nowadays can be done with lots of pulse sequences, which is possible. This I showed you how decoupling helps when there is no decoupling, gated decoupling without NOE, with NOE, without NOE, and finally a broadband decoupling with NOE. Finally, decoupling helps you with NOE to get a very good signal to noise ratio compared to the one which is without decoupling and without NOE. And decoupling can also be done with pulse sequences. Number of pulse sequences are available now. We use what is called waltz, GARP, MLEV, varieties of pulse sequences are utilized. And we can use decoupling by various methods like this. And I do not want to go into the details of the decoupling. Now we will concentrate on spin echoes. So that was the information which I wanted to give as far as the decoupling is concerned. No, I don't want to come back to the decoupling, but basically idea is there, simple. You can do broadband decoupling. Of course, you may ask me a question. I did the heteronuclear decoupling. Can I not do homonuclear decoupling? Yes, it is possible. But homonuclear broadband decoupling is not possible. Moment you bring the magnetization to a transverse plane, and if you start applying RF pulse, you are going to disturb the magnetization. It is not possible. But selective decoupling is possible. What happens is, let us say AX spin system is there. Here is A and this is X. Two spins are there. So what you can do is, in the AX spin system, you know, we already saw that there are two doublets like this in the AX coupled spin system. Now I can start selectively irradiating this proton. When I apply the power such that it is just sufficient or more than this coupling strength, and exactly when I sit on this at the center of this doublet, then what happens when this power matches this condition, this collapses into a singlet. Okay, this is what is called selective decoupling. Broadband decoupling we have to do in a different way, that is called pure shift NMR. But this is a two spin example I took. You can take more. If there are coupled spins, number of spins can be coupled. And if they are all different peaks coming at different position, like here, there is a bunch, here there is a bunch of peaks, then you can selectively irradiate here, apply RF power here, and see the effect somewhere in the spectrum. Let us say this is 4-line pattern. If this proton is coupled to this and also coupled to this, no problem. It will be coupled to proton A and proton B, let us say. When a hit at this frequency, the second radio frequency pulse, then coupling of this to this proton is broken. So then instead of doublet, it will become only a doublet. So selective, now I know this proton is coupled to this. On the other hand, I can also do this. Selectively, I can decouple this proton. Then if this and this are coupled to this proton, now when I hit separately this, again, this coupling will get collapsed and you get a doublet. You understand the logic? So very important thing we can do in the case of protons also, homonuclear decoupling, selective decoupling. So this is just concept of decoupling. You remember what basically we do is, when the irradiated spin we saturate, so that the coupled spin will not see the irradiated spin in either of these two energy spin states, alpha or beta, and he is going to see only the average spin state, or more or less it is a state which is not degenerate, which is a degenerate state, I would say, so that no separation of the energy level. As a consequence, it appears as if there is no coupling. Okay, with this now come back to carbon 13. In the spin echo sequence and the decoupling, this is what we do. This is what we understood what is a spin echo. Now we are looking at carbon 13. At the same time, I am trying to do the decoupling here. Now I will represent this spin vectors, what happens to different pulse sequences, like we explained for spin echoes for in previous example. You can try this thing, what happened to different carbons which are attached to different protons, like CH carbon, CH2 and CH3. All those things can be now discussed like this. For example, if this CH carbon, CH2 and CH3, you will see how they evolve in different parts of the pulse sequence as a function of time. Let us look at the evolution of J coupling with CH proton. What is happening to after 90-degree pulse? Magnetization is coming to XY plane. It starts moving. This is the up to this, in the pulse sequence. Up to this we know. Now this we already discussed. Now I'm going step by step to see what happened to CH vector. carbon coupled to proton. It is only a doublet. Carbon will become a doublet because of CH. Now at this stage what happens? At this stage what happens? At this stage what happens? For CH vector we will see. Now the moment to bring the magnetization to one axis, X or minus Y doesn't matter. Now I'm just giving a drawing. It is brought to one of the axis from Z axis to X axis. Let us say by applying appropriate 90 pulse. Allow it to evolve for a time TD. Exactly what happened, as I said, one is a fast moving component, other is a slow moving component. There are only two components for CH because it is a doublet. Doublet comes because of alpha and beta spin states of protons, right? So one alpha component of this carbon 13 start moving like this, and the beta component start moving like this. You understand? So one is moving this, the other is moving like this. And then at any given instant of time, let us say, I can find out the angle theta by which these vectors have moved. I can understand, I can find out if what is the angle by which this has moved at any given instant of time. Okay. Now, each vector start evolving under the coupling of J and CH. How much it has evolved at a given time theta is given by this simple expression. Please remember this. The theta during the how much it has moved, the angle in which these vectors have moved, the theta angle can be given by pi into TD into JCH. It depends upon three factors. Pi, of course, one full rotation is pi, and it depends upon the delay, how much time you have waited in this pulse sequence, how much time you have waited in this pulse sequence. Okay, and then what is the strength of the coupling? Depending upon the strength of the coupling and the time for which you have waited in the TD, I can calculate how much these vectors have moved. Okay. Now let us consider a situation when the time delay is exactly equal to 1 over 4j. Fit it to this equation now. Time delay is exactly equal to 1 over 4j. Then TD is equal to 1 over 4j. J will go. It will become pi by 4. Then what will happen? It has moved by 45 degrees. Okay, it is exactly moved by 45 degrees when TD is exactly equal to 1 over 4j. Just simply plug this value into this. 1 over 4j, jj cancel out. 1 over 4, it is 5 by 4. Okay, pi radians is 180 degrees, so pi by 4 is 45 degrees. Okay, it is moved by 45 degrees. Now wait for some time. Let us say the TD is now not 1 by 4, 1 by 2j. Put TD into the equation. Now what is going to happen? They are rotated by 90 degrees. So the fast moving component, slow moving component, the one which is moving like this, the one which is moving like this. Now one comes along plus z axis, one comes along minus z axis. They are now exactly apart by 90 degrees. Okay, this is what happens. Not exact apart by 90 degrees, they moved by 90 degrees with respect to the axis it was there. Between them, there are of course 180 degree difference. But each vector has moved away from the axis in which it was tilted initially by 90 degree pulse by 90 degrees. Okay. After the time delay of TD, a 2 pi pulse is applied. Now, after this time delay of TD, a pi pulse is applied. This results in the rotation of the magnetization along x-axis. Thus, pi pulse inverts the magnetization. You understand? I'll show you the vector diagram like this. So, that was only the explanation I was giving you of what happened to the magnetization at a different time. Now, let us say at any given instant time when it is rotated, I'll apply, let us say, after a certain time, let us say when it is at 554, I apply a 180 pulse. In the like a spin sequence we explained, it gets completely inverted. So, it starts rotating like this, 180 degree. When you apply 180 degree pulse, what is going to happen? It inverts the magnetization. So the magnetization, the one which was here, now comes in this axis. If they were in the first and the third quadrant, fourth quadrant, now it came to second and third quadrant. Now what is going to happen? They continue to move in the same direction. But now we will do one important thing. What we can do is, this is a vector, this is a vector. Can I not resolve this M into two components? One component here, one component here, one component. So there are two components, one along this axis, one along this axis. So if I take the component along x-axis and y-axis, these opposite components, this and this, what will happen? The vectors in the opposite direction gets nullified. Only component along this axis starts adding up. This is a vector addition. They start moving in this direction, and after some time they start adding up. The opposing component will go because they are out of base by 180 degree and cancel out, and there is no magnetization generated by these two components because they cancel out. Whereas our receiver is kept here, let us say x-axis, it will not give magnetization, but only this component will give magnetization. Understand the point very clearly. Alpha and beta vectors now resolved into its vector components. Opposing components gets nullified. The components moving in the same in the one of the axis like this, not opposing, not non-opposing components, they start adding up. Okay, and that is the one which generates signal in the receiver. The vector components in the same direction add up gives a singlet, and second TD and the decoupling of these two vectors generate is applied to refocus communication and get a good signal phase. What it means is, now the second one, you give some time delay here. After some time, now without giving it delay, now after if you start decoupling, they are all in different phases. So what you have to do is you have to give another time delay so that all of them completely get refocused here. Okay, that is what the thing you do. Give a time delay so that all the spin vector starts getting refocused and chemicals should get refocused. Then there is no phase distortion. You are going to get a signal with a good phase. That's what is to be done. Now let us see the signal intensity as a function of time. See, when you measure the signal intensity as a function of time, when the exactly time delay is equal to 1 hour j, signal intensity is 0. When it is exactly 1 hour j, the signal intensity is negative maximum. What does it mean? The variation of signal intensity is following a cosine function. It means it is a cosine function. It starts with the maximum, comes here 0, negative, and then go. It is oscillatory function, follows a cosine function. Now this function, it is 0 for the TD values of 1 over j, 2j, and maximum minimum for multiples of 1 over j. Of course, you may know, I ask me a question. Different carbons have different couplings with proton. How do I know it is j? Approximately you have to take the average and say they are nearly same. Take the average value and then you have to do this experiment. So this is what happens for CH carbons. Remember, in a pulse spin echo sequence with decoupling in the pulse sequence we observed, we saw at exactly time delay is equal to 1 over 2j, signal intensity is 0. At exactly 1 over j, signal is negative maximum. This is the important point which you must understand. So what we will do is we will come back and what happened to CH2 pulse, CH2 vector, CH3 vectors we will understand. Then we will know how we can utilize this to identify, edit different carbons depending upon the number of protons attached to it. We'll come back and continue tomorrow.